All right. So this diene here is electron rich. It has 2 alkenes, so double the electron density than an alkene. Okay, so that's electron rich diene, and then this one on the right is attached to some fluorine atoms. So that's going to be electron poor, our dienophile. All right, so this one wants to combine with a diene to form a participate in the Diels-Alder reaction. Okay, so we combine these two. So this reaction actually occurs at relatively low temperatures. You don't even need to heat it that high, 30 degrees Celsius. So when we do that, compared to the other one we saw, we need 200 degrees. This one only takes low temp. Okay, and we get the product in much greater yield. Okay, so at high temperatures, you also have to worry about decomposition. So that's why the yield for the top one here is like 20%. This one is racemic. I didn't draw the rest of the molecule here. So CF3. So you have mixed stereochemistry here. Racemic. Okay, and it's greater than, it's approximately greater than or equal to 60%. Okay. All right, so those are our two, that's how we come together here. Okay, so you can also have the similar situation where you take let's use our same diene. Okay, so we use the same diene and it combines with, instead of alkene, let's use an alkyne. So you can also react this with alkynes. So they work for both carbons here, carbon functional groups. Okay, so you heat this one up. Okay, so what's happening here is one of the double bonds is coming from the alkyne, shifting the double bond over to the central carbon bond, and this will push these arrows and attach to the carbon of the alkyne there, and then you get a non-conjugated alkene, where the alkenes are on opposite sides of the ring. They're not connected through one double bond, or through just one single bond, sorry. And then again, this one, since we've used two, we use an activated dienophile and diene, we get a pretty decent yield, about 60% in total. Okay, so so the kind of takeaway here is you have a diene and at least a alkene, an electron poor alkene, or electron poor alkyne. Okay, so you can see here that in both our examples, this group has an electron withdrawing group, and my alkyne has 2 electron withdrawing groups, 2 groups with oxygen atoms in there, so that makes them particularly reactive. Okay, so to get this reaction to go, you need the one to be, more nucleophilic, and the other one to be really electron deficient, so it can actually make this reaction go quickly. Okay. Are there any questions on the arrows here, the final product? Practice drawing your arrows. So wherever you see an arrow point to, draw a new bond between where the arrow lands and where the arrow starts from. And you can see here, if we circle our arrows, this bond is now this bond right here. And then this bond, this green bond right here, is now forming this bond between the two molecules there. Okay, so I find it helpful if you just look where the arrow is going and where it started from, you're going to draw a new bond, just straight line to the new molecule. Okay. Are there any questions on those? Are there any questions on why this one is electron poor and why this one's electron rich? Are there any questions about that? Those two? Okay. So this is Diels-Alder. Okay, we will actually do an experiment with Diels-Alder. We'll do two. One we'll do in the lab, and then one we're going to add some reagents together, and then we're going to stash it away, cover it, leave it in the dark, and let it react for 1 week, and come back next weekend, check on it, and work it up. Okay, so that's we'll be doing this reaction, and the classic experiment reaction in organic. So we'll be doing that one. Okay. All right. So how do we know if a group is electron withdrawing? How do we know if the dienophile is electron poor? So you might be wondering, how exactly do we determine if a group is electron withdrawing? So let's go over that. So I go over this because in the next chapter, we are going to go over reactions with benzene. And benzene reactions can be controlled by specific substituents on them. Okay, so groups that are electron withdrawing by resonance. So the whole theme here is resonance now. That's why we practice it so much last semester. All right, so if there is a double bonded O group attached to our alkene, okay, this double bond O can take the, can withdraw electrons like this. So we get one resin structure where the carbon now has no octet and it's positively charged, and there's an R group right here. Okay, and then we can shift the electrons over. We take one bond and shift it to the right, and now we have now a more reactive position on the alkene, showing that it's actually partially positive. Like that. Okay, so we see this with any group, any carbon or alkene bonded to this double bonded oxygen atom. All right, so that's one of the examples for electron withdrawing group. The other common group we'll see for these reactions is a not a nitro, but a triple bonded CN group. So we have something like this as well. So you can also cause electrons to be delocalized if the electrons are from a triple bond. So we can expose the carbon here. The carbon has a positive charge with this double bond present. So now this nitrogen has a negative charge. We put those lone pairs on the nitrogen. And then the double bond can move right here. And now the double bond carbon atom can now be right there. And now I'll put a little dot here to indicate that's a carbon on the structure. So we still have a carbon right there. N minus. So you see here the electrons can be withdrawn from the alkene into the nitrile, the CN group. And then that causes our carbons here to be electrophilic. So that's how we make the dienophile more reactive. Okay? So the more electron withdrawing groups or electronegative atoms you have on the dienophile, the more reactive it is. Okay. So resonance here helps us explain that reactivity. Okay? All right. So this is where the dienophile. Now let's talk about the relative reactivity of dienophiles and dienes. Okay, so let's first go with dienophiles. So those are your alkenes. Okay, so you have a regular old alkene, not very reactive. So the more carbon groups on the alkene, the less reactive it will be. All right, less reactive than that, less reactive than the simplest alkene, less reactive than the trifluoro group here, trifluoromethyl group. And then that's going to be even more, less reactive than you have a pi bond or, nitrile groups here, CN groups. And the more CN you have, the more reactive it is, okay? So you want more groups with pi bonds. More groups of pi bonds make the dienophile more reactive, okay? Dienophile. All right, so you want more electronegative groups on there. Okay, CF3 is still reactive, but it's reactive by resonance. Sorry, not resonance, induction. Sorry. All right, now let's look at the reactivity of dienes. So the more carbon groups, electron donating groups, remember alkyl groups or any carbon single alkane chain, those are the most reactive. So we've got one methyl, then you have two methyl groups here, very reactive. All right, then if you have something that can donate through resonance, that's even more reactive. Oops, sorry, let's undo that. I meant a double bond right here. Okay? So, carbon groups, they donate electron density, but then if you have something that can do resonance and push electrons into the diene, that makes it even more reactive. So this is the most reactive, and this is the diene part of Diels-Alder. All right. So here we have increasing reactivity. Okay. All right. So we went over the reactivity of electron withdrawing groups. Let's go over how do electron donating groups work by resonance. Okay, so let's do that next. All right. So we have our list of dienophiles, dienes. Now let's do, I know I'm using this. Electron donating groups by resonance. All right, so the most common one is when you have an oxygen group with its lone pairs kind of bonded through the diene here. So you have the diene, and the oxygen can actually move its electrons and push these outward. So it's pushing more electrons in there, and then you can have a resin structure with an actual negative charge. So that's more reactive than having no charge. Like this. So that's an example of electron donating by resonance. And then we'll see a lot of groups could do this. So some are more stronger than others, and we'll see that in a few chapters. Okay, so if we use these two examples, we use this to kind of write a different reaction. All right, let's use this diene here and this electrophile of the alkene, electron deficient alkene. We have this pair of compounds. Now, if I heat this for 100 degrees for 3 hours, I get this compound in great yield. The adduct, the cyclohexene ring here. All right. Okay. So we get this in 90%. So when we get that 90% yield, and also since this, because of the Diels-Alder reaction, it actually occurs from both faces of the alkenes. So remember how alkene reactions, they can approach from the top phase or the bottom phase? This happens too, so you get 90%, and it's actually a racemic mixture. Okay, so those are we talked about electron donating groups, and then by resonance, and then electron withdrawing groups there. Okay, are there any questions on that example? Okay, so now let's talk about the stereochemistry of the Diels-Alder reaction. So there is some stereochemistry involved here. So let's talk about that next. Okay. All right. The stereochemistry of the Diels-Alder reaction. All right. Number one, highly stereospecific. So it's highly stereospecific. It favors approach, so you get one stereoisomer from the reaction, okay? It adds through the same face of the double bond, so syn addition. Okay? So stereospecific refers to like the orientation of the initial stereochemistry, okay? And then here the stereochem of the dienophile is retained or is kept in the product. All right. So let's use our example here, our ethene, and then we have this cis alkene with both of these groups on the same side of the double bond like this. Okay, so here we have a cis dienophile. All right. So we heat this up to 150 to 160 degrees Celsius. And this takes 20 hours, so it's a slow reaction. 20 hours. And you get primarily this product. So the two carbon groups here, the CO2, CH3 groups, they are cis in the product. So the stereochemistry is retained. All right, and then you get the hydrogens pointing up, hydrogens pointing down, like that. All right, so you get this and 68% yield. All right, so this is just the name of it. You don't have to worry about this name, but it's dimethyl cis 4 cyclohexane. So now when we have carbon double bonded groups, the alkane chain, or the longest alkane chain, is no longer the parent name. It now is dependent on these carbonyl groups, or these C double bond O groups. So 1, 2 dicarboxylate. So they look like carboxylic acids, but they're esters. Dicarboxylate. Okay, so this is the cis product. Okay. Now what happens if you use the trans alkene instead? What if we used a trans alkene instead of a cis alkene? So let's make this, let's change the structure of this a little bit and make it trans. Okay, so we have this alkene. We're still using the same alkene, but we're going to make this the cis, instead of the cis dienophile, we're going to make that a trans dienophile. So the groups are going to be trans here. So the H is here, opposite sides. So we have the trans dienophile right there. So we still have the same kind of product, but it's just in a trans relationship now. So different, actually a different compound. All right, so I didn't draw this before, but let's draw the arrows just to practice. Like that. And then this one. So we had to rearrange those bonds to show the transformation there. Okay. Now the trans isomer, a little shorter reaction time, but higher temperatures, 3.5 hours, and then 200 to 205 degrees Celsius. All right, so now we can get the other product. And now, since this is in a trans relationship right here of the dienophile, the products are no longer, this molecule is no longer symmetrical, so you're going to get a mixture of enantiomers. All right, so we get CO2, CH3, hydrogen, and then the carbonyl groups are going to be in a trans relationship, just like they were in the reactant. So you get this, and it's in pretty good yield, 95%, and it's racemic. So you can attack both sides of the double bond as these molecules approach. And when we get to a specific example, I'll talk about how the mechanism works here. I'll show a little video. All right. So the name of this product, very same exact thing, except we have dimethyl trans 4 cyclohexane. 1, 2 dicarboxylate. carboxylate. Okay, and this is the trans product. Yeah, Catherine, what's up?
What if we use a alkane-based parent name when it's an alkene?
Oh, my bad. Sorry, I should. Thank you for bringing that up. My bad, everyone. It's an alkene, it's a cyclohexene. Thank you. Thank you for catching that. Sorry about that. Cyclohexene, yes, right. There's an alkene, so we should just name it cyclohexene. Thank you very much. Okay. So you'll notice here in our diene, so look at the molecule on the left. Do you remember the conformations we talked about? What conformation is this in? Is it the S-cis conformation or S-trans conformation? If we think about, I don't know, I thought we talked about it somewhere. Yeah, we talked about it over here. All right, so look at the conformation of the diene that we just drew. Is it in the S-cis conformation or S-trans? So let's compare it to, let's go all the way back to the bottom now. So what orientation is this diene in? Is it the cis conformation or the trans conformation? Yeah, the cis conformation. So the diene has to get into the S-cis conformation. So sometimes these require high temperatures, and that's because you need some energy to kind of force it into the more unstable isomer. So you have to get it to go to something less stable. All right. So number 2. Okay, the diene reacts. In the S-cis conformer. All right. So if your molecule is probably going to be in the S-trans conformation, so we have to equilibrate it to the S-cis conformation to get it into the right orientation. Because if it's not in this conformation, the double bonds, the p orbitals, are too far away to react and form a stable ring. Basically, the geometry won't be, it'll just give you an awkward kind of geometry, and the bond angles won't be nice. Remember when we talk about bond angles, if the bond angles aren't ideal, it's going to be very hard for that ring to form. All right, so it's going from the S-trans conformer, to the S-cis. So the S-trans is unreactive. This is the reactive conformer, okay? That's how it reacts. Okay? Now, what if your ring forces you to be in the S-trans conformer? Like this diene in this cyclohexene ring. Okay, so no matter what you do, no matter how hot you heat it, this ring is locked in place, so it's not as flexible as it can't rotate. So this will not be a reactive diene, so non-reactive diene as it's drawn. So in order to make this reactive, you would have to you would pretty much have to figure out a way to kind of get the double bond in another place, but that's hard because this is in a conjugated position. So it might be hard to do that. Okay, so non-reactive diene in the Diels-Alder reaction. Okay, so it has to be in the S conformer. It's stereospecific, highly stereospecific. Okay, and we said the dienophile is the stereochemistry of the dienophile is maintained. Start out trans dienophile, trans product, cis dienophile, cis product. Okay. Now the last point, I think the last point here. Yes, so the last point here, bullet point 3. Okay. The stereochem of the diene is also retained. Okay. All right. So let's first draw a different diene here. All right. Okay, so there's a few positions I kind of want to annotate here. So when something is pointing away from the double bonds, so it's kind of going outside of the double bonds, you know, towards the kind of the north and south extremities here. This is considered going outside, because if I flip it on its side, it's going to go outside or out and away from the alkenes. And so these two groups are going to be outside. Okay, so they're pointing outside. So when I do a Diels-Alder reaction, it's actually going to look, maintain the same stereochemistry. So let's do NC, CN. All right. So here, this is called tetra, cyano, ethene, because it's an alkene. This structure on the right, the left, methyls, so the CH3 groups are cis. So they're pointing outside, okay? So we call this actually, so since there's two double bonds, you can kind of see here, the carbon group is pointing up direction. The other carbon chain is pointing down. So we call this first double bond trans. We indicate the stereochemistry here. And then we look at this group here. The bond is going up. So that bond is going up. And in this carbon, this bond is going down. So again, for the second double bond, this is also trans. So we got trans for the first double bond, trans for the second double bond. And since if we number them 1, 2, 3, well, sorry, no, let me go back. I numbered incorrectly. 1, 2, 3, 4, 5, 6. My alkene starts at 2 and 4. So 2, 4, hexadiene. So this is the tricky part. When you have multiple alkenes, you drop the A and E ending completely, and then you write it hexadiene. So the ene part it comes with the di prefix. Okay, so that's the trans-trans isomer. Okay, and if you heat this up, you get your cyclohexene ring. Okay. And then since these two outside groups are the same, they're going to have the same stereochemistry. And one isomer you do get is when these two groups are pointing out. So when they're on the outside positions, usually how they depict it in books, usually these two groups are going to be pointing down. In the structure here, okay? And then the rest of these are CN groups. You don't have to specify the stereochemistry because there's no stereo centers at this carbon atom. And we don't have to write racemic because if we did draw the isomer, then the enantiomer, it will still be the same. right? You could flip this molecule and both those dash bonds would be wedged. So this is the only product you would see. All right. And then let me just compare this with another reaction. So here, the methyl groups, methyls, end up cis. Okay. So now let's contrast that with a slightly different diene. Okay. So let's draw it like this. Okay. Now, the only difference here, one of the methyl groups is now pointing inward. So this would be considered still outside. This now is inside. So if one's pointing outside, one's pointing inside, you're going to get different stereochemistry. So this is actually going to look trans. Okay? The methyl groups will look trans. Okay. So in this case, we have if we circle here and circle here, this group is pointing in the same direction as this group. So both those groups now, this is going to be cis. The first one is cis. And then if we look at this carbon now and this carbon, this one's pointing up, the carbon group, this carbon group going downwards. So this is the cis trans 2,4 hexadiene. So when you have multiple double bonds, what they do in nomenclature is they specify the stereochemistry of each. So you know exactly how the double bonds and the groups are arranged. So that's what you do there. Okay, but let's now draw our same tetracyanoethene here. Okay, and then the product, it looks the same. It's just a different stereoisomer of the diene. But what we have here instead, one of the methyls will appear up now because it's pointing in the inside, and the hydrogen is pointing on the outside. And then on the bottom carbon, the methyl is sticking out, or in the back, sorry, and the hydrogen is coming out in the front. And then the rest of the molecule, you have CN, CN. And again, there's only one stereoisomer because if you rotate this molecule around 180 degrees, this methyl group will end up dashed when you flip it, and this methyl group dash will end up wedged when you flip it. So you get the same molecule if you flip it again. So this one's also, it doesn't look symmetrical, but you can make it symmetrical by just flipping the molecule. Okay, so that's the stereochemistry behind the dienophile and the diene. So it actually is maintained. Okay. Yeah, Catherine, what's up?
Explain how the green circles are cis.
Yeah. Sorry, let me just. All right, let me just erase this. So let's erase this one again. Yeah, let's go. Okay. Where was that? Boop. All right, so let's just focus on this double bond right here. So this for this alkene, right? This carbon, so this carbon of the alkene, and this carbon, right? They're pointing on the same side of the double bond. So they're going like in the same direction right here. So it's pointing this way, and it's pointing this way. So when they're pointing the same way, remember that's like saying this. That's a cis alkene, right? Versus it looked like this. So sometimes it's hard to see in the ring when you have a lot of other stuff going on. So that's why I kind of highlighted there. So that's why that one's the cis. Because these two lines for the carbon atoms, they're they're bonded in this. They're oriented in the same direction, so it's going to be a cis alkene in that regard. Yeah. All right. Okay, so all right, just stay with me for a bit more. Let's talk about the typical dienes you would see. You can expect, like, not just here on the homework, and usually what's tested. Okay, so these are the typical dienes you see in a Diels-Alder. All right, so let's go over this, and we'll take a little break. All right, so 1,3, so this is 1,3-butadiene, okay? So just 1,3-butadiene, the simplest diene we can have. And then you have 2,3-dimethyl 1,3-butadiene, where, getting ahead of myself, drew the product instead. So the dimethyl one, when they're on the interior carbons, then you can have the methyl groups on the terminal carbon atoms to do Diels-Alder. Okay, and then some of the common ones we will see in lab is these ring structures. So you have 1,3-cyclopentadiene, okay, and then 1,3-cyclohexadiene, like those. So those are common ones. And then these other two, these last two, they typically react faster because they're already locked in the S-cis conformation. The other ones are probably going to be in the S-trans, so they will have to rotate a bit to react. And another reason why these ring ones are particularly good is that if the methyl group is positioned wrong, it can actually slow the reaction. It could retard the reaction or slow the reactivity. All right, so for example, if we had this diene right here, why do you think this might be a slow reactive diene? What do you think is going to happen if these two groups I just drew here, they kind of exist in the same plane? Remember alkenes, things attached to alkenes, right? They're flat and planar. So this methyl group and hydrogen, what do you think they're going to do? They're going to bump into each other. And what's that interaction called? When two of these groups, they approach each other and they repulse each other because of, their electron clouds get too close, their bonds get too close. What was that called? Steric? Yeah, steric hindrance, right. So that's still a thing, especially in reactions of alkenes and just in general. So you have steric hindrance here. The hydrogen is small though, so it won't actually make it completely dead. Like, remember tertiary alkanes, or halaalkanes, they don't do SN2. It's like virtually no reaction. But a non-reactive diene is when we have both of these pointing in the same direction in the diene. So two methyl groups. So here, the methyl groups crowd each other so much that it's virtually non-reactive, right? So again, steric hindrance. But right here, it's even more pronounced that it doesn't even react. So if you see something like this, two methyl groups there, and it looks like a Diels-Alder, it's actually just no reaction because of steric hindrance. You would write that. So that's the reason. So what happens here is I think this is so unfavorable that it will force it out of the S-cis conformation and go to the S-trans, and it'll be locked in conformation. So it can't actually go back to this state because it's just so unfavorable. Okay, so let's stop there, take a little break. I want to take a bit to talk about the next thing and show a video. So let's take a break, a little 5-10 minute break here, and then we'll come back and talk about the endo rule for Diels-Alder. All right, endo. Thank you. All right. All right. Let's talk about the fourth aspect of the Diels-Alder, and that's something called the endo rule. So endo, in the same meaning that endodermic means you absorb heat or heat goes within a system. Okay. So 4 here is something called the endo rule. So I just want you guys to know about the endo rule because it relates to what we talked about before, kinetic versus thermodynamic control. Okay, so endo rule is it states that the endo product or endo adduct is the preferred product. Is the preferred product. Like say you have a reaction and you let it run for a short time, the kinetically controlled product is endo. So let's talk about endo and exo additions. Okay. So there's a trick to see what product is endo and exo, and I'm going to go over a few examples to show that. All right, so bear with me here. We're going to draw a propeller type molecule. So we're going to draw a structure like this. It looks like kind of like a puckered cyclobutane. But what actually happens is you're going to have a carbon atom that comes up and above and bonds with the thing behind on the other side. And this right here becomes like this. All right. So if I have this alkene here, I'm just demonstrating what endo and exo looks like. So here, let's hydrogenate this double bond. And we have palladium on carbon. Okay. So let's redraw our propeller looking thing. Okay. Welcome, welcome. All right, let's just keep this. Oops, didn't mean to do that. Okay, so remember in hydrogenation of an alkene, you can get the hydrogens or deuterium. So we use deuterium in this case. To point both up, there's a syn addition here. Okay. Or you get the other enantiomer. OMG, nope. Didn't want that. Okay. And then, or the deuteriums are pointing downwards, okay? So when you have this situation, this is what we call a bridged cycloalkane or bridged hydrocarbon. It's bridged because above the main ring, there's like an arch, and that's the bridging piece of the molecule, okay? So look at these two groups. The bridge, so this is called the bridgehead. So the bridgehead and the deuterium atoms, would you say they're cis or trans? Cis, right? They're both pointing above the ring, right? Good. So that's cis, all right? The cis product is called the XO product. So this is actually the XO. So the adduct just means the ring, or, the product of this reaction, of something adding to the molecule, okay? So this is the thermodynamic product. Okay? So that's the XO. Now this one is called endo. So what XO really means is that the deuterium atoms are pointing away from the space that this ring occupies. Okay, so it's pointing away, kind of away from the bridgehead. Now endo, this is the endo adduct, and the endo adduct is for the kinetic product. So that's the product that forms the fastest. Okay. Now compared to this bridgehead and these deuterium atoms, they look like they're trans in a trans relationship. They're opposite sides from each other. Okay. All right. So that's the endo rule, and then I'm going to let's see. Anyone else not sign in here yet? So that's the endo adduct, the kinetic product. Okay. So in Diels-Alder, there's two possibilities. The deuteriums. Well, this is not Diels-Alder, but you'll get two kind of things here: the exoadduct or the endoadduct. So I drew these to kind of visualize what endo and exo are. So now let's apply this to actually a Diels-Alder reaction. So now this is our Diels-Alder reaction. All right. So we're going to have this cyclopentadiene here. All right. So this can be initiated by light as well. And then we're going to have our dienophile here like this. Okay. So the beauty of this, one process gives you exo, and then one process gives you endo. All right, so let's draw this bridgehead again. Like that. Okay, so if both the bulky groups of the dienophile So these two carbonyl groups, if they point up and are cis to the bridgehead, they are going to be the exoadduct. So see, these groups are pointing up, and the hydrogens are pointing down. All right, so this is exo. They are pointing away, in the same region of the bridgehead. Okay. Now, if we do the same reaction, but we change the conditions here to heat instead of light, that actually gives it more time. It actually makes it occur faster, and so you don't have time to equilibrate, so it's not going to be a thermodynamic process. So this is the kinetic process. Kinetic process. This is the thermodynamic process. So when you have light, sometimes you react it for a long time, and you give it time to equilibrate, you get the exoadduct thermodynamic product. And this one, you get the endo product. So you get the endo, and what happens here is that the two bulky groups are going to point away from the bridgehead. So they're pointing away and down from the bridgehead here. Okay, and the hydrogens are pointing up. So they're pointing up and away from the, I probably should have drawn that a little better, but sorry about that. The hydrogens are pointing up and away towards the bridgehead, and bulky groups are pointing down. All right, so this is endo. But to kind of visualize this a little better, let's watch a little animation here where these two groups come together to form the product. Okay, so I'm going to play that right now. All right, I have it. Here we go. So, not exactly the same carbonyl groups, but they're pretty similar. We just don't have that methyl group there. Okay, so let's watch this and see what happens. Okay. So they're just showing the arrows right now. So you see the double bond O's. They're going to orient away from that central bridgehead. So they're pointing away from that CH2 group up there. And it's approaching in a way where those double bonded oxygens are underneath the alkene bonds. So that's actually a favorable arrangement of the orbitals. But I don't expect you guys to kind of reproduce that or anything. Okay. So see, that's how it approaches. And you notice the double bonded O's, they're directly underneath the little triangle bridgehead part. So that's the endoadduct. If it was exo, the H's over there, they will be on the other side. They'll be basically switch places. These carbonyls will point outward instead. But it's these interactions with those p orbitals that give the preference transition state and the endoadduct. Another argument I like to make, I don't see this argument made online or in books, is that the bridgehead is pretty bulky, so the bulky groups want to point away from it or approach away from the top bridgehead part. So I think that's maybe a good argument for the endoadduct. Okay, are any questions about this so-called endo rule? It has to do with the arrangement of these conjugated pi systems, really. And if you have groups that have double bonds, they can actually interact with other double bonds in the transition state, and that stabilizes this formation here. Okay. I won't make you draw that, though. Draw the transition state. It's a little little complicated. We'll see on this next page that drawing it is particularly challenging. I tried to draw it like 5 different times, and I had to scratch out my work. You see right here, scratch it all out. So it took me a while to actually draw this transition state. But I'll show you now in a little more detail what this transition state looks like. Okay, so let's go back to here. All right. So what does this transition look like? All right. So let's do our same molecule here. So I'm gonna try to write this in like perspective. Not very good at doing this perspective drawing. All right, so this is coming out at you. It's kind of a 3D sort of arrangement here. All right. So here's the double bonds. This is the CH2 group. Okay. So look at this single bond here. And this single bond. They are cis across the double bond. So these 2 bonds are cis. This is a single bond. Okay. Now, what happens here is that I have my diene on the very bottom here. And then here is my carbonyl group of the previous page. So that's where the dienes are oriented, and the dienophile are going to be oriented. Okay. So what happens here is that this bond is going to start forming a bond to that carbon. This bond is going to start forming a bond to that carbon. And we can see here the hydrogens. So look at these 2 hydrogens. It's pointing away from the diene. All right, and these 2 groups over here, see how it approaches underneath the diene. It's going to, these 2 groups are actually underneath the diene, so these are pointing towards the diene. So this group is actually oriented underneath and towards the diene, okay? So this is what happens, and we get endo addition. Okay. And that's what we get for, oh, actually, no, that's right, isn't it? Oh, you know what, guys? I think I forgot something here. Let's scroll it back a little bit. I forgot to put these double bonds. My bad. Right here. I knew something was missing. All right, so those should be where the double bonds are at. Because these are the 2 new bonds we form. These are the 2 new bonds we form. And then this double bond also forms there. So those are the 2 bonds. Those are the bonds that actually form. So let's, I don't want to give the wrong impression there. Okay, so there we go. All right, so now this endo addition, it looks like we draw the ring. All right. Okay, hopefully that's clear there. All right. So the hydrogens are pointing up here, and the 2 carbonyl groups here are pointing down. So they're down and away. So that will be our endo addition or endo adduct. And then these 2 hydrogens are pointing up and away. And then these two groups are been added. That's called endo addition. Okay, so if we draw these 2 hydrogens over here, the hydrogens on the cyclopentane pentadiene, we can see that the CH2 groups is cis to the single bond in the diene of the diene. And that's what I pointed out right here, these two arrows. So the CH2 group and that single bond are actually cis to each other, okay? But we see here that the CH2 group, it is trans. The CH2 group is trans to the bulky groups right here, the bulky groups right here. Of the dienophile. And that's by looking at the product in our ring here. The bulky groups is the C double bond O, CH3. Those groups are trans to the CH2 group in the final product right there. Okay. All right, so that is our endo addition. So that's how we contrast endo, but what would exo look like? Yeah, Captain.
Wait, so just to clarify, the CH2 group you're mentioning is the top of the bridgehead, right?
Yeah, this one right here. Yes, this one. Is the top of the bridgehead. Yes, so that CH2 group is the one I'm referring to. Right. Good. Okay. All right, let's contrast this with exo addition. What would exo look like? So exo addition, the bulky group of the dienophile is on the same side, cis, as the CH2 group. All right. Can I just copy this? Actually, no. Let's write it together, because you guys have to draw it. All right. So the CH2 group is still pointed downwards like this, and then we still have this alkene, but the alkene is oriented where the H's now are oriented underneath the diene group. And then these bulky groups are pointed away from the diene. Oops, my bad. Like that. And then you have, in the transition state, these groups are approaching. Again, this group is approaching this from the top face. Okay, so now what we have here, these are now away from the diene. And these hydrogens right here are toward the diene. So the Diels-Alder actually prefers this orientation of the diene one way, okay? And then if you let it go back and forth, it can actually go back to the exo adduct, so it can be fine-tuned to what product you want, the XO edition here. All right, now for XO edition, let's now wrap up. All right, now I'll shade it a little bit to indicate. This is my bridgehead. All right, we can actually draw the hydrogens here too, just to show it. And that's what I'm referring to as the CH2 group here. Okay, so now the hydrogens are pointing downwards. And then the two bulky groups here are now situated wedged and on the same side of the ring as the bridgehead. Like that. So this is called XO addition. Okay, so that's exo, endo. All right. On your homework, they really don't really specify endo. So all I'm really looking for is, can you draw the Diels-Alder product? This included drawing with the bridgehead, without a bridgehead. So look at the examples we did for Diels-Alder. Okay. Advanced treatment of this, we would actually talk more about this, but we're not going to for that. Okay, so I just have a few more. Just one thing I'll go over, and the last thing I want to talk about is just regio, a little bit of regiochemistry here. So I'm going to talk about that, and then we'll take the quiz. Okay. All right. Regio selectivity of Diels-Alder. Okay, so say we have these two scenarios, okay? So Diels-Alder, you can actually have regioisomers. Where, how does the double bond add, and what's the orientation of this carbonyl group here? Okay, so does it line up towards one direction of the diene, or does it line up in the other direction? So to determine how you pick which of these products is the major product. Is it this one? Or is it this one? So if your dienophile is not symmetrical, you can get potentially three, more than one regioisomer. All right, is it this one or is it that one? So how do we pick? Which one is the major product? So that will be our question. Which is the major product? Okay, so you have to look at both parts of the reaction. So let's look at the diene. So in order to answer this question, you have to draw resin structures and ask yourself which one is more favored. So let's go to the diene first. So here, which form is better? A or B? So let's just look at two resin structures here. We have one where the lone pair. Let's see here. We move the double bond. Here is the positive charge, and we move the lone pair over here. So that's we move the double bond from the bottom and move the top top pi bond into a lone pair. Is that more favorable, or is this more favorable? So this would be structure B. This is structure A. Let's go to reverse. We draw this here. Okay. And now this carbocation is formed at this position, and this is a secondary C+. All right, and the anion is right here. So I want you, just for next time, think about which of these form is better and compare to resin structures. And we'll talk about that next time on Tuesday. All right, now it's time to take the quiz. Okay, so I'm going to leave this up for a few minutes. All right, so put everything away. Only thing you should have out is the quiz, pen, pencil, or eraser. Nothing else is allowed. Oh yeah, sorry. A and B, there is deuterium here. All right. All right, when your desk is square, you may begin. Good luck. Reactions of all kinds. Okay. Anyone else not signing it? Emily, I don't think you did. iPad away. Good luck, everyone. Okay. All right. Good luck.